Good morning. This is very strange without having music in the background, but Pretzel is not working today, so I don't know if it's me or if it's in general. But anyway, we're going to dive into it. It's so quiet. It's so quiet. I don't know if I can handle this. Okay, I'm going to try though. Let's see. Get status. So there were two things I wanted to do before I started work on the inheritance thing. The first thing was the whole, let's see if I can pull it up here, visit call expr. Yeah, I wanted to switch it over to using this style, but still somehow being able, because this is shorter, right? We can just grab this and then we just have a single thing that checks the arguments. Right now, I have this code duplication where I check the arguments here if it's a function, and I check the arguments here if it's a class, and it's basically identical code. The difference is we have to do class.instantiate versus function.call. And so I was thinking what we could do is extend the call the call interface, so that it could take a class as well. And then maybe an option class would be it, because then functions don't take classes. So it would be, we could just pass none, right? But then classes would take an RC clone of the class, and that way the constructed object would have a reference back to the class it was constructed from. So why don't we take a look at figuring out how to do that? I think all we have to do is say in locks callable. I think we can just extend the call thing here to take a class, right? Interpreter arguments class, maybe? Is that the right order? So class would be an option of an locks class. An option of RC locks class. Right, and then just putting that in there, then this will allow us to find all of the missing locations for it. All right, if I try to compile now, everything that uses call will break, and I can just put none. Oh, we don't have locks class. Locks class star. Okay. So here, right, so we can just put in a class here. Option RC locks class. And just ignore it for now. Here, right, and this will just be, again, ignored class, option RC locks class, and then we'll have to add it in. And then here, in native clock, yeah, we don't need any of that, right? For the native. Oh, that's the other, right. So like I said at the beginning, there were two things I wanted to fix. I wanted to fix this interface to the call infrastructure, and then B was the fixing the native stuff. I forgot to mention that at the beginning. So option RC locks class. I'll have to use that. And then here's where we call. Here's our first call, and this says instantiate. We can just put, since this is the init function, we can just pass in none. What's this? Right, that's what's defined. And then here, this is what we're going to clean up, so we don't have to worry about this. And then that's it. So, okay, so this now builds. If I get rid of this chunk of code here, right, this whole thing, and then uncomment that, we should have something close to what we want, except we need to be able to pass in the class that we're from. Right. Do I already have I just have func here, right? Call func, call func. Yeah. I guess what I can do is just extract the class right here and just pass in a none for the other one. So if I say call func and class like that, and I can just say none, just to get it to type check. I can put none here, but I need to switch that over to be an RC in a second. Oh, RC is not here. Use standard RC. Oh, right. Oops. This has to change as well. So this needs option RC locks class. And this should be none. Like that. Okay, so this type checks. That's good. So we got as far as getting the class stuff in there. We still don't have the native functions and we still don't instantiate objects. So we need to fix that. Which means this call func on the class needs to change, right? Because right now, if I try to run it, it won't allow. Let's try it. Cargo run class foo, and if I say var f equals foo to instantiate it, it says try to call the class. So that means that the call infrastructure is working, but we need to fix this thing. Where is it? Oh, it's right here. Okay, so instead of this, we need to call the initializer, which means we do need to pass everything in, right? So where's instantiate? We can just call instantiate since we already have it written. We can change this to self instantiate, and then it's interpreter arguments, and then class unwrap, right? Because we're going to be passing it in. Now we're down to 2 warnings, and that warning is the native functions warning. Okay, so let's see if this works now. Class foo, rf equals foo, and it panicked. Oh, it unwrapped on a none, right? Because now we have to fix the interpreter. Call func, right? Because we want to pass in the class instead of passing in none. Okay, so this is just an RC clone of call e. Oh, sum. It's got to be a sum. Nope. What am I trying to match against then? It's going to be the class. Oh, is it just a clone of C? Value moved here. Oh dear, we can't do it this way, right? We have to split it into 2 steps, otherwise Rust gets cranky. So you can say let class equals this, and then we can just say some class. Yeah, okay. Rust gets cranky if you try to do it all in one line, because maybe it's unclear as to what happens first. But anyway, so this seems to work. We get the clone of the RC here, put it there. We get the actual class from there and put it there, and then we call it here. And now let's see if this works. Class foo, var f equals foo, print f. It's an instance of class foo, so it all seems to be working. So I should be able to say f field equals 1 and see it in there. And so, yep, it's field value of 1 on a class foo instance f. Okay, that's that. Wow, that wasn't as bad as I thought it was going to be. Clippy's okay with it. A lot of changes. but mostly just adding this class argument. Yeah, and then we stripped out all this duplicate code, which is great. It was nice to strip out code. Yeah, that was pretty straightforward. Git add source, git commit, cleaned up call interface. Okay. So the next thing, before we get into inheritance, the next thing I want to do is fix up the native functions. Because right now, if I say cargo run, and I say print clock, undefined variable clock, and that's because we've commented out this thing here. I can't create a new native clock. So I think what I want to do is just have another object type. Maybe like that. And you got to put it down here. And then we have to create a locks native. Oh, we already have native functions though, right? We already have the native here. So that means we need to create pub struct locks native, which is going to take a function of rc dim locks callable, and then pub, impl locks native. No, if this is a pub func, then we can just create those on the fly. Use create native functions. Oh, and we have to create a toString for it. Okay. Callable. Callable interface has. Wait, here it is. Just call an arity. That's all it has. Okay. So I guess we can just say native, right? If we just we create a display impl for it. Like this. Oh, right. Use standard format and format display. And now what? Oh, it doesn't implement debug. Oh, do I have to hand implement all these? Probably, hopefully not. Derive, debug, clone, and partial EQ. Nope, I got to do it by hand. Okay. So hopefully this does the debug. The next one is going to be, does it complain about clone or just partial equal? Just partial equal. Okay, so we can implement that. Impl partial. Oops, I forgot the pop out. Diablo. Sorry. I missed your message earlier. There we go. Forgot to pop my pop out. Pop out my pop out. Okay, partial equal for locks native. And this is just going to be the standard EQ of self and other is self, returning bool, and we're going to book, returning bool, and returning RC pointer EQ. I am trying to add native functions back into my locks interpreter because I took them out a couple of days ago when I was fiddling around with the class interface. Self func and other func. All right. This still doesn't check. Oh, because I don't want to do that. Clone somehow? Clone somehow can do it on its own. Interesting. Variant is never constructed native. Right, okay, so now we want to construct that variant. Okay, let's do that. Source interpreter, and that's under clock. We can do this, we can do this, and then we can change this to native, and like say locks native, func is this thing, and now, whoops. And as soon as I'm done getting this native function stuff working again, I'm going to start on chapter 13 here. So we have a new native clock followed by a closing brace for the locks native. We have locks native, we have define. Okay. And of course it fails. Oh, because I don't have native functions in here. Use crate. I put them in their own file back when I thought, oh, it's got to be RC. Back when I thought we would have more than just one native thing. Oh, there's still 2 warnings though. Unused import. Really? Oh, in interpreter. But we're using it right here. We're using locks native and native clock. Okay, let me cargo clean. Cargo build. No, it still thinks we're not using it. Oh, because I have it in there twice. Okay. Yeah, that was a problem. Okay, so now if I say cargo run, can I print the clock? Can only follow functions classes. Oh, right, because I didn't add it to my call export. All right, we need it here. We need object native n is going to be sum n and none. Oh, Lozzie, thank you for the follow. Some reason my notification sound didn't sound. Let me do a test follow real quick here. Oh, my sound is down too low because for some reason Pretzel Rocks isn't working today, or it wasn't working when I tried to start streaming, so we have no music, and so my sound settings are all off. But Lozzie, thank you for the follow. Much appreciated. Oh, you heard it? Oh, okay, so maybe my monitor is too low. I'll crank up my monitor. All right. Trait is not implemented. Oh, because it's n.func, right? No. n.func.clone, because it's an RC, so I should be able to just clone it cheaply. Yeah. Okay, cargo run. Print clock. There we go. Okay, so now this is the time of day clock in milliseconds. You can see here the 9, yeah, 3, 4, 5, 5, 6, 7, 7, 8. Yeah, this is the second. This is where second starts. All right, so that's working now. Get status. Get, we can Clippy. I don't know why I still have that in the cargo format there. Oh, comparing trait object pointers compared to non-unique vtable addresses. We had this issue before. and then I fix it in a different way. See, I'm doing it here, and Rust isn't, or Clippy isn't complaining about it. What's the difference? I mean, it's identical code. What am I doing wrong? Class. No, native. I mean, the code's identical. Why does Clippy complain about this one but not about these? Impl partial EQ. So callable locks function, and that's it. Oh, right. We did it this way. That was what we did. Okay, source native. So we can cheat and do it that way, and maybe that'll make. Where is it? Here, it's right here. That'll make Clippy happy. Kind of wacky, but it does the trick. Clippy. Here we go. Okay, git status, git add source, git commit, -m native functions are working again. Okay. Very good. So now we're ready to start right into inheritance. That only took 24 minutes. Grox Alpha, hi. Welcome to the stream. Okay, so, and this is the last chapter of part 2. So once we're done with this chapter, we're all done with the AST version of locks. And then not next week. Next week I'm going to do the, I'm going to switch back to the roguelike. But the week after that, I'm going away. So the week after that, then we'll start with the bytecode version of locks. Okay, so can you believe it? We've reached the last chapter of part 2. We're almost done with our first locks interpreter. The previous chapter was a big ball of intertwined object orientation features. I couldn't separate those from each other, but I did manage to untangle one piece. In this chapter, we'll finish off locks' class support by adding inheritance. Inheritance appears in object-oriented languages all the way back to the first one, Simula. I've never actually used Simula. So I don't even know what Simula code looks like. Oh, it looks like Pascal. Okay, interesting. You're doing a survey, Grox, and you haven't advice any advice against procrastination. Never do today what you can put off until tomorrow. I think that was the, isn't that the phrase? I have no advice for anti-procrastination because I procrastinate about everything. Even on things that'll take me 5 minutes to do, I just keep putting it off and putting it off. Why? Because I'm dumb. So my advice against procrastination is don't be dumb. Like me. Early on, Christian Nygaard and Ulla Johan Dahl, it's pronounced Ulla Johan Dahl, noticed commonalities across classes in the simulation programs they wrote. Inheritance gave them a way to reuse code for those similar parts. You could say all those other languages inherited from Simula. Hey-yo! I'll see myself out. Diablo says sounds like ADHD. Yeah, I probably have a mild form of it. Superclasses and subclasses. Given that the concept is inheritance, you would hope that they would pick a consistent metaphor and call them parent and child classes, but that would be too easy. Way back when C.A.R. Hoare coined the term subclass to refer to a record type that refines another type, Simula borrowed that term to refer to a class that inherits from another. I don't think it was until Smalltalk came along that someone flipped the Latin prefix to get superclass to refer to the other side of the relationship. From C++, you also hear base and derived. I'll mostly stick with superclass and subclass. Super and sub mean above and below in Latin. Yeah, I understand that. Set theory, subset is contained by a larger superset. Okay, so you have supertypes and subtypes there. In statically typed object-oriented languages, a subclass is also often a subtype of its superclass. Say we have a donut superclass and a Boston cream subclass. Oh, all this talk about donuts is not nice. Grox Alpha says, what's this project about? Sierra Horror is a wizard. I don't know who that person is, actually. I should probably learn about them. The project Grox is about crafting interpreters, and what I'm doing is I am attempting to port it to Rust, and I'm most of the way there. Let me just throw a link in the chat, and you can take a look if you like. Our first step towards supporting inheritance in locks is a way to specify a superclass when declaring a class. There's a lot of variety in syntax for this. C++ and C# place a colon. Java uses extends. Python puts the superclasses in parentheses after the class name. Simula puts the superclass's name before the class keyword. Do we even have an example of that? Class glyph. Oh, glyph class char. Is that a sub? Is char then a subclass of glyph? Glyph class line. Yep. Yeah, this is very, very Pascal-y, isn't it? It's like Pascal plus plus. He's a big name like Knuth. Wow. Then I am really out of touch because I know Knuth, but I don't know horror. Grox says, I think I'm going to save this book. Yeah, it's a really good book to go through. I went through compiler programming back in college, and it's been a while. So this is reinforcing what I learned, and is also extending what I learned because we didn't do classes and inheritance and all that kind of jazz. This late in the game, I'd rather not add a new reserved word or token to the lexer. We don't have extends or even colon. We don't? Oh, wow. So we'll follow Ruby and use less than sign. Okay. I mean, it's not that hard to add a new reserved word. Why not just throw it in there? That would have been fun to go back and reinforce what we learned during the scanning and parsing phases, right? For adding new keywords. But I guess we're going to go with less than. Yeah, the Dragon Book, Diablo, that's the first one I used. By Aho, Sethi, and Ullman. There's an updated version who has a fourth author whose name I forget. This is the Dragon Book. Monica Lamb. That was it. I didn't want to continue the stream without remembering that name. All right, so we're going to use this syntax. We have a class donut, and we have a class Boston cream, which inherits from donut. To work this into the grammar, we'll add an optional clause in our existing class decl. So class identifier followed by 0 or 1. That's what the question mark means. 0 or 1 less than followed by identifiers. After the class name, you can have a less than followed by the superclass's name. The superclass clause is optional because you don't have to have a superclass. Unlike some other object-oriented languages like Java, Locks has no root object class that everything inherits from. So when you omit the superclass clause, the class has no superclass, not even an implicit one. We want to capture this new syntax in the class declarations AST node. Okay, so we're going to modify. I think we're clean, right? Yep. We're going to modify our class here. It's going to have token name. It's going to have a list of all the methods, but before that, we're putting an expr. Of superclass, right? You might be surprised that we store the superclass name as an expr variable and not a token. I'm not surprised because I don't understand yet. The grammar restricts the superclass clause to a single identifier, but at runtime that identifier is evaluated as a variable access. I see. Diablo says, I followed it, meaning the Dragon Book, to do a toy language. Makes me appreciate not throwing my hat in the ring. Yeah, so making a language is, I mean, there's a whole craft to it, right? And it's not just the programming part, which is what crafting interpreters is talking about, but there's the design part of what should the language look like. That was left out of this book, just to get the programming part in. It would be nice to see a book on designing languages, but I think that's a niche profession inside an already niche profession, right? Wrapping the name in an expr variable early on in the parser gives us an object that the resolver can hang the resolution information off of. Okay, so this is a very important point summarized in one little variable, why we're using the one little paragraph, why we're using expr instead of a token for the superclass name. It's to support the current design of the interpreter's code. Diablo says, Rust is the last language we'll ever need. Yeah. It's a great language, but I'm sure in 30 years there's going to be an even better one. Or society is going to collapse because of global warming, whichever. The new parser code follows the grammar directly. All right, so in parser, let's save this and then go to parser. In class declaration, what does this look like right now? We say expect class name. Okay, so before the opening brace, we're going to add this code here. Let superclass equals if self is match token type less. So this is the less than token consume token type identifier expect superclass name, and then we're going to say right, because we're going to need an else none. It's going to be a sum, which means this thing needs to be an option, which means we have to go back to this thing here and change this to be an option, because if there is no superclass, we have to be able to stick a none in there. Like that. Okay. So this has to be okay of RC new of expr variable, which contains an RC new a variable expr, and it's going to just contain the previous, and I forget what it is. Is it a token? Variable expr. Where's our variable expr? Yeah, just token with name. Okay, so up here we go. Name is going to be self previous dupe. Close that, close that, close that, close that, close that. Wow. Does that check? It does not. Oh, this should be some, not okay. Diablo says, I'm betting on societal collapse. Yeah, I wouldn't be surprised. All right, so now we're missing superclass in here. So we just toss it in, and we're done. Wow, that was easy. Once we've possibly parsed the superclass declaration, we store it in the AST. That's what I just did there to make it compile. If we didn't parse a superclass clause, the superclass expression will be null. In our case, none. We'll have to make sure the latter passes check for that. Oh, the later passes. We'll have to make sure the later passes check for that. The first of those is the resolver. Okay, so let's go over to the resolver. Inside visit class statement. Define statement name. And then just before begin scope here, I'm going to say if let some superclass equals statement superclass. I probably have to ampersand this, right? Then self resolve. Ooh, it's an expert, right? Expert superclass. And this does take a question mark. I just saw it down here at the bottom. Okay, so that's that, and that's that. So does that check? No. Oh, expected RC found R and ampersand RC. So if I do this, will it move it or will it be okay? Yeah, I have to do it this way. Deref or clone? I guess clone. Yeah, okay. We're cloning the RC, so that's cheap. The class declaration AST node has a new sub-expression, so we traverse into and resolve that. Ooh, we'll see .ka. Potentially, however, humans are resilient and adaptive creatures, else we would never have made it this far given our previous living conditions. Yeah, the question is what form will society take? That's the big thing, right? I make my living off computers. If electricity and computers no longer exist post collapse, then I'm gone. All right, I don't know how to do subsistence farming yet. Maybe that's something I should start learning. The class declaration AST node has new sub-expressions. Right, so I did that. However, locks allows class declarations even inside blocks. Oh, okay. So it's possible a superclass name refers to a local variable. In that case, we need to make sure it's resolved. Before even well-intentioned programmers sometimes write weird code, there's a silly edge case we need to worry about while we're here. Take a look at this. Class oops. Diablo says all programmers become farmers. Yeah. Hopefully I'll be living in an area which permits farming. Meaning the environment permits farming. Okay, so if I do class oops, what happens? Class oops. I mean, it created an oops variable with a class whose name is oops. Oh, where's the superclass? Doesn't the locks class isn't it supposed to have a superclass? What went wrong here? If I look at class expression, oh no, class statement. Oh, right. It has its own, it does have the name oops in it. The value oops. Wait, where does the superclass gets? Oh, we haven't modified the interpreter yet. Right, so this isn't even doing anything. Okay, I need to ignore that. There's no way this will do anything useful. And if we let the runtime try to run this, it will break the expectation the interpreter has about there not being cycles in the inheritance chain. The safest thing, I think this is the first mention of this in the book. It probably should have been introduced earlier. The safest thing is to detect this case statically and report it as an error. Okay. So let's detect it in visit class statement. Safe and superclass is not null, and we can just check here if. Of course, this is just the simple case. This is not showing the case where you can have chains of class things that end up being circular. Right? Okay. I'm just going to put this in here. If superclass.name.asString equals statement to name as string, self error, super class name. I think I have to ampersand that, and then just say a class can't inherit from itself. So we can test this out pretty easily. Oh. Superclass has what in it? Superclass is an expr. Oh, but the expr has to be deconstructed. Right, this says statement superclass name Lexeme. We have the superclass which has the variable expr, which we don't know yet. Okay, so we actually have to extract that. If let sum, no, if let, not object, statement, right? Oh no, it's an expr. Expr variable v equals superclass, and then we can say v dot name. Oh, that I can deref. And then self error. Oh, we want to put the superclass name in there as the token, right? So we can just say v. Yeah. Okay, so let's see if this actually runs. Let's do this oops guy here. Yeah, a class can't inherit from itself. Good. Assuming the code resolves without error, the AST travels to the interpreter. Very good. So this is where we're actually going to do the work. So before we do environment define, which is this line here, we're going to do the superclass business. If let sum superclass, little statement superclass, then we're going to say let superclass. Will Rust let me shadow this way? Do I need to question mark that guy? I do. And then say if. Now we're checking to see if it's a locks class. I guess I can say if let object class C equal to superclass here, then we're good. We don't have to throw anything. Else return error, locks error, runtime error, superclass. Oh, we need the name. I might have to change that. Superclass must be a class. This looks odd. There's got to be a way to, I guess I could use match locks result. I changed it from locks error to locks result a long time ago, and now I can't even remember it. Oh, right, because I overwrote that. Superclass expr, and then the superclass expr. And name is unknown field. Again, because I need to pull out the expr class thing from it to get that to work. But this I don't like. This is very awkward. If there is a superclass expr, then this value is it's an RC of expr superclass. No, it's an RC of yeah, it's an RC expr, which is expr variable expr with a name. That's what we're looking at here, of superclass expr. So in order to pass the name in, I have to pull this thing out of it. Here we pass it into evaluate this thing. We pass it into evaluate. If it evaluates as something other than a class, that's all we do. I mean, we have to be able to do something with it, right? We're going to do something with it at some point. Because this is setting it to null here. So I think up here I have to say let superclass equal this, and then this just returns some C. I think that's what needs to happen here. Else if let some expr variable v equals superclass expr. I don't think I have to clone it here, right? I can just do this. Then I can say v.name here. Else panic could not extract variable expr. And right now I'm just going to put an underscore here, so semicolon, yep. Okay, this expression has type ref expected, okay. And so deref on that finally. Yep. If maybe missing an else. Oh, right. So if this does not, then we just say else none. Wow, that is some ugly code. I don't know if this comment is helping or not. How's that? Okay, this works. I mean, it compiles, and that's half the battle. If the class has a superclass expression, we evaluate it. That's this here. Since that could potentially evaluate to some other kind of object, we have to check at runtime that the thing we want to be the superclass is actually a class. Bad things would happen if we allowed code like this. Assuming that check passes, we continue on. Executing a class declaration turns the syntactic representation of a class, its AST node, into its runtime representation, a locked class object. We need to plumb the superclass through to that too. We pass the superclass to the constructor. Okay, so where's our constructor? Right down here. So we say object class RC new, locks class new, statement name as string, and then methods, and we're going to add the superclass to that. Which means we have to go modify locks class new to accept that. constructor stores it in a field. So we're going to say superclass is going to be an option of an object. And that object is going to be, let me do this and see if this builds. Oh, right. Oh, this is an RC. Some C, some clone. Oh, no, no, no. Yeah, I guess we want an RC. Let's do that. Nope. Expected enum object found locks class. Oh, okay. Maybe we're just passing in locks class then. That makes it easier. Yeah. Okay. And now we have to store it. So we can just say super class is equal to option RC locks class. And we can just say super class. How about that? Brilliant. Okay. With that, we can define classes that are subclasses of other classes. Now, what does having a superclass actually do? Nothing yet. Okay. So that was section 13.1. Cargo run. I should be able to say class foo, and then say class bar inherits from foo. And print this out and see we have class foo. We have class bar with superclass of some locks class named foo. And if I add something to, oh, it just has the methods. Oh, let me try that. Class, it should inherit the methods through the RC. Foo func. Print foo. Right? Oops. What did I miss? Uh-oh, did I break my parser? Oh, underscore is maybe not okay, class foo, print foo. Yeah, underscore is not a valid, okay, we should add that. So now if I look at the environment, we see class foo, or foo is a name. It has a class of foo with the name foo and a function with the name lowercase foo, function foo. Okay, so if I say class bar, inherits from foo, right? And now I take a look, I can see here's bar with no methods, but its superclass refers back to the foo with the method of, yeah, okay, good. Okay, so that's all working, but I don't think I'll be able to say, if I say var b equals bar, b dot foo. Yeah, it doesn't know how to look it up in the superclass yet. So that's what we're going to get to next. So let's check in with Clippy, and let's commit these changes. Section 13.1. What was section 13.1 called? Superclasses and subclasses. All right. So 13.2, inheriting methods. Inheriting from another class means that everything that's true of the superclass should be true more or less of the subclass. In statically typed languages, that carries a lot of implications. Subclass must also be a subtype. And the memory layout is controlled so that you can pass an instance of a subclass to a function expecting a superclass, and it can still access the inherited fields correctly. Fancy name for this hand-wavy guideline is the Liskov substitution principle. Barbara Liskov introduced it in a keynote during the formative period of object-oriented programming. All right, locks is a dynamically typed language, so our requirements are much simpler. Basically, it means that if you can call some method on an instance of the superclass, you should be able to call that method when given an instance of the subclass. In other words, methods are inherited from the superclass. Right, that's the whole point. This lines up with one of the goals of inheritance, to give users a way to reuse code across classes. Implementing this in our interpreter is astonishingly easy. Let's see how astonishingly easy it is in Rust to do this. So in find method, we do this. Okay, so I guess we need to do an if here, right? So methods is a hash map string object. So we can say if let sum method equals self methods get name. We're going to return sum method. This is doing method name cloned. Why am I cloning the method? It's an object. I want to see what breaks, because I've forgotten what breaks. And then else if self superclass, let sum superclass equals self superclass. And we're going to return superclass dot find method of name. Else we're going to return none. Yeah, so this is expecting an object, and that's why I did a cloned on it. And now I can't do that. Wow. Okay. I guess cloned is for options. So let's give it a try. Let's donut. Let's copy this in. And see if we can call bossandcream.cook. Yeah, it works. That was simple. That was easy enough. Clippy doesn't mind any of that. Section 13.2, and that's just called inheriting methods. I thought it would be a little tougher, but it was pretty easy. Calling superclass methods, 13.3. In find method, we look for a method on the current class before walking up the superclass chain. If a method with the same name exists in both the subclass and the subclass one takes precedence or overrides the superclass method, sort of like how variables in inner scopes shadow outer ones. That's great if the subclass wants to replace some superclass behavior completely, but in practice, subclasses often want to refine the superclass's behavior. They want to do a little work specific to the subclass, but also execute the original superclass behavior too. However, since the subclass has overridden the method, there's no way to refer to the original one. If the subclass method tries to call it by name, it will just recursively hit its own override. We need a way to say call this method, but look for it directly on my superclass and ignore my override. Java uses super for this, and we'll use that same syntax in locks. Here's an example. All right, so let's extend our donut code. And this won't work because we don't have super. Yeah. Okay. If you run this, it should print this, but we have a new expression form. The super keyword followed by a dot and an identifier looks for a method with that name. Unlike calls on this, the search starts at the superclass. With this, the keyword works sort of like a magic variable, and the expression is that one lone token. But with super, the subsequent dot and property name are inseparable parts of the super expression. You can't have a bare super token all by itself. So the new clause we add to the actually, I think we already get a syntax error right there. It should be a expect expression, just like this line here. Cargo run, super, yeah, same thing. So the new clause we add to the primary rule in our grammar includes the property access as well. So true, false, nil, this, number string, identifier, grouping expression, or super followed by dot followed by identifier. Typically, a super expression is used for a method call, but as with regular methods, the argument list is not part of the expression. Instead, a super call is a super access followed by a function call. Like other method calls, you can get a handle to the superclass method and invoke it separately. All right, that's fair enough. So the super expression itself contains only the token for the super keyword and the name of the method being looked up. The corresponding syntax tree node is thus: token keyword, token method. We're clean. So let us add super token keyword, token method. Following the grammar, the new parsing code inside our existing primary method. Okay, so we're going to look at parser. Here's primary. Primary is getting very long. That's okay. So it's just before this. Here we go. If self is match, token type, super. Token let keyword equals self previous. Here we did self previous literal clone. That's because it's a number. Where else are we doing previous? Yeah, I do self previous dupe. Okay, let's do a dupe. All right, that's the previous is the super keyword we just matched against. Self consume token type dot expect dot after super. And then let method equals self consume token type identifier expect superclass method name, and then return okay expr super oh no rc new super expr, and then we're going to say just keyword method. This might work. If not, we'll fix it up. All right, a leading super keyword tells us we've hit a super expression. After that, we consume the expected dot and the method name. All right. Let's see if this checks. And we have a resolver issue and an interpreter issue, but that's it. So that other code works. All right, now we're going to talk about semantics. Earlier, I said a super expression starts the method lookup from the superclass, but which superclass? The naive answer is the superclass of this, the object the surrounding method was called on. That coincidentally produces the right behavior in a lot of cases, but it's not actually correct. Gaze upon this. All right. I'm going to put this as a test, a bit of test code here, abc.locks. Translate this program to Java, C# or C++, and it will print a method, which is what we want locks to do too. So if we call c.test, C inherits from B inherits from A. B's test is calling super method, which is a method. C's super method, if C just followed the inherits thing, C's super is B, so it would print B method instead of A method. I see. When this program runs inside the body of test, this is an instance of C. The superclass of C is B, but that is not where the lookup should start. If it did, it would we would hit B's method. Instead, lookup should start on the superclass of the class containing the super expression. In this case, since test is defined inside B, the super expression inside it should start the lookup of B's superclass A. The execution flow looks something like this. This is very complicated. We call the test on instance of C. That enters the test method inherited from B. That calls super method. Superclass of B is A, so that changed the method on A. And the program prints A method. Thus, in order to evaluate a super expression, we need access to the superclass of the class definition surrounding the call. Alack and alas, at that point in the interpreter where we are executing a super expression, we don't have that easily available. We could add a field to lock's function to store a reference to the lock's class that owns the method. The interpreter would keep a reference to the currently executing lock's function so that we could look it up later when we hit a super expression. From there, we'd get the lock's class of the method and then its superclass. And we actually with my refactoring this morning, at the beginning of the stream, we now do pass in the class when we call, or we could. But okay, let's keep going with this. That's a lot of plumbing. In the last chapter, we had a similar problem when we needed to add support for this. In that case, we used our existing environment and closure mechanism to store a reference to the current object. Could we do something similar for storing the superclass? Well, I probably wouldn't be talking about it if the answer was no. So yes. Does anyone even like rhetorical questions? One important difference is that we bound this when the method was accessed. The same method can be called on different instances, and each needs its own this. With super expressions, the superclass is a fixed property of the class declaration itself. Right. I get that. Every time you evaluate some super expression, the superclass is always the same. That means we can create the environment for the superclass once when the class definition is executed. Immediately before we define the methods, we make a new environment to bind the class's superclass to the name super. When we create the lock's function runtime representation for each method, that is the environment they will capture in their closure. Later, when a method is invoked and this is bound, the superclass environment becomes the parent for the method's environment, like so. Boom, 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 boom. That's a lot of machinery, but we'll get through it a step at a time. Before we can get to creating the environment at runtime, we need to handle the corresponding scope chain in the resolver, right? Because the resolver and the interpreter need to be in sync on this. All right, so in visit class statement, if statement superclass is not null, so that's down here, right? I know we have here resolve statement superclass, which is this line here. But we've already extracted to here, so we can. I think we can safely do it here. We can say self begin scope, and then scopes dot borrow dot last dot unwrap dot borrow mut dot insert super to string true. Self scopes. Yep. Don't go away yet. Don't go away yet. Okay, so then we're going to have to add an end scope. Oh, I see. If statement superclass is not null, an end scope. So we're going to have to do the same thing here. We don't actually have to do that. We can just say is sum. Yep. Okay, so that checks out. It's a minor optimization, but we only create the superclass environment if the class actually has a superclass. There's no point in creating it when there isn't a superclass, since there'd be no superclass to store it in anyway. Yeah, so technically we could just put a super in there every single time, right? We don't have to check if, but whatever. I guess that avoids having a super keyword available. But yeah, okay. We're good. With super defined in a scope chain, we are able to resolve the super expression itself. Okay, so that's what we're going to do here is visit super expr, and that's going to be a super expr here. And what's this going to do is just resolve local. Self, resolve local, wrapper, expr keyword. Very simple. We resolve the super token exactly as if it were a variable. The resolution stores the number of hops along the environment chain that the interpreter needs to walk to find the environment where the superclass is stored. This code is mirrored in the interpreter. When we evaluate a subclass definition, we create a new environment. Okay. So this should all check, and now we're over at the interpreter. In visit class statement, which is up here, after environment define, we're going to say if let some superclass expr equals statement superclass, right? And then we're going to swap out the environment. Environment equals new environment, environment. Oh. Right, I have to use that new within closing business. Yeah. And it's actually setting the current environment, right? This is on the instance of the interpreter itself. So how does this supposed to work? Because we're not doing like an execute block. I think we do a replace, right? Let mut e equals environment new within closing self environment borrow clone. I'm just following this line here. And then we're going to say e dot define super with our superclass expr. Probably have to clone that. And then we're going to have to say let and closing. And then we'll say here we're going to return some self environment replace with e, else none. Except probably not. Did I miss a closing quote or something? Because this is all purple now. Okay. Oh, it has to RC new ref cell new environment. Okay. Like that. And then at the end, after we, just before the assign, we'll have to undo it. right? Here's the class, and then here's the assignment. And we undo it here. Okay, so then if let sum enclosing our previous equals enclosing self environment replace with previous. I have no idea if this is going to work, but let's give it a shot. Expected an object, found an expr. Yeah, okay, so the superclass needs to be an object. Oh. And we're expecting it to be a locks class, right? Here's the thing that we want. Okay, so superclass is what we want, right? It's already a sum C. So, yeah. If let sum C equals superclass. I think that's what we want. Some S, sorry. And we can just put S in there. Object class S. Mismatch types. Yeah, okay. So that builds. It's always good when it builds. I have no idea if it works, but it compiles, and then we have to handle the visit super expr, right? So inside that environment, we store a reference to the superclass, the actual locks class object for the superclass, which we have now that we are in the runtime. Then we create the locks functions for each method. Yeah, that's already part of it, right? Those will capture the current environment, the one where we just bound super, as their closure, holding on to the superclass like we need. Once that's done, we pop the environment. We're ready to interpret super expressions themselves. There are a few moving parts, so we'll build this method up in pieces. So here's our first piece. This is super expr. And then we're going to get a distance. Let distance equals. And I think we already have a distance thing somewhere else. So let's take a look at that for comparison. Self locals borrow get wrapper unwrap. I guess we're gonna assume it's not a none. It's not null. We assume we check here to see if it's local or global, right? But I guess here there's always going to be a local for it. So okay, and then I guess this will panic if it doesn't, which means there's a bug in our interpreter. All right, so then we grab our class itself. Let superclass equals self environment borrow get at distance super. Do I have to put a something else in there, or will that just work? All right. Oops, borrow has to be done this way. And expected usize found a usize. Fine. And unwrapped, this can't be called on result. Okay, I just put an OK in here just to get it to stop complaining. Oops. object nil. Oh, now we have, okay. Yeah, now we have borrow checker issues. I've let some ref. Oh, really? Let's try that. No, we still have an error. Expected RC found reference. Oh, okay, so I can just clone it. I can clone the RC and we're all happy. Ah, now we have a problem here. Creates a temporary while still in use, and then the temporary is freed. Really? It creates a temporary, but it's... Oh, I can just do that, right? And that copies it. Yeah, okay, now we're good. Boy, oh boy. First the work we've been leading up to. We took the surrounding, we look up the surroundings classes superclass by looking up a super in the proper environment. When we access a method, we also need to bind this to the object the method is accessed from. In an expression like donut.cook, the object is whatever we get from evaluating donut. In a super expression like super.cook, the current object is implicitly the same current object that we're using. In other words, this. Even though we're looking up the method on the superclass, the instance is still this. Unfortunately, inside the super expression, we don't have a convenient node for the resolver to hang the number of hops to this on. Fortunately, we do control the layout of the environment chains. The environment where this is bound is always right inside the environment where we store super. Okay, so we can just subtract 1 from the distance and we're there. Okay, good. The warnings are because I'm not using distance and object. Why are there 4 though? What's the extra warning there? Oh, we are not using expr yet. I'm sure we will pretty soon. Lox function method is superclass find method expr method luxim. Offsetting the distance by 1 looks up this and that in your environment. I admit this isn't the most elegant code, but it works. Writing a book that includes every single line of code for a program means I can't hide the hacks by leaving them as an exercise for the reader. Okay. Now we're ready to look up the bind method starting at the superclass. All right. And now we're going to actually use expr here. Expr method. And I think the way I do luxim is just as string, right? And then we're going to return OK of method bind object. That's not going to work, is it? Why superclass? I did an OK here, right? So, but I still think it's an option object. So do I have to go OK on wrap? Right, now superclass is an object, so we have to destructure that. So if I guess we can destructure it here, right? Yeah, let's do it like that. If let sum c equals this, superclass sc is this. Okay. Then we're going to pull out, because right now that's an object. If let sum, no, object class equals superclass. else panic, unable to extract superclass. Ah. I was going to complain about moving, or if maybe missing an else clause, right? Huh. Is there... Okay, it gets us part of the way there. Expected stirs found string. And then bind. Method not found on option object. Okay, so method needs to be extracted as well. If let some method is blah, 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 then do that. Else panic method not found in superclass. Oh, wait, no. We want this. Okay, I'm going a little too fast. I just want to get it to compile. We do want to throw if let object, it's a method, so what's that type? Locks function? Probably. This should be the panic, right? Method was not a function. Okay. And then else, we're going to return an error. All right. This is almost exactly like the code for looking up a method of a get expression, except we call find method on the superclass. That's basically it, except of course we might fail to find the method, so we check for that too. Okay, so here's where we're checking for that. So this is locks result, runtime error, expr method, lexeme. We do want to find out, yeah, so here's expr method. Like that, and just undefined property this dot this. Oh, I have to format it. And comma expr method as string. How's that? Still not good. Method not found in object because I got to change that to func. Oh, no, I have to change this to func. And then it's going to tell me something's wrong with object, found enum. Oh, because this needs to be an unwrap. Fine. Still, expected token and expected format. Okay. And details on formatting. Okay. All right. It compiles. There you have it. Take that Boston cream example earlier and give it a try. Assuming you and I, especially me, did everything right, it should fry at first and then stuff it with cream. Okay. What do we got? We have the donut. Cargo, run, donut. Huzzah! So that worked. This is the super call, and this is the local call, right? Let's take a look. Boston cream cook, super cook, fry until golden brown, and then print pie full of custard. So that works. And what about this ABC example? And it prints a method, which is what we were hoping for all along. Okay, so let's get this checked in. What's this? Oh, okay. So it's working, but let's finish up the invalid parts. Invalid uses of super. We're almost done. Almost done. As with previous language features, our implementation does the right thing when the user writes correct code, but we haven't bulletproofed the interpreter against bad code. In particular, consider this. What if you call super on a class that doesn't have a superclass? Cargo run. Let's see what happens. Cargo, sorry. Class foo cook super cook. The resolver resolved everything. Foo cook. What happens? It panicked. 165, where we just did an unwrap here. Yeah, so we assume, like I was saying before, it's assuming it's going to work, but okay, what if it doesn't, right? This class has a super expression, but no super class. At runtime, the code for evaluating super expressions assume that super was successfully resolved and will be found in the environment. It's going to fail here because there is no surrounding environment for the superclass, since there is no superclass. The JVM will throw an exception and bring our interpreter to its knees. Well, this does. Heck, there's even a simpler broken usage of super. Super not even in a class. Yeah, same line, 165. We could handle errors like these at runtime by checking to see if the lookup of super succeeded, but we can tell statically, just by looking at the source code, that eclair has no superclass and thus no super expression will work inside it. Likewise, in the second example, we know that super expression is not even inside a method body. Even though locks is dynamically typed, that doesn't mean we want to defer everything to runtime. If a user made a mistake, we'd like to help them find it sooner rather than later. So we'll report these errors statically in the resolver. First, we add a new case to the enum we use to keep track of what kind of class is surrounding the current code being visited. All right, so we'll pop into the resolver. And class type, none, class, or subclass. We'll use that to distinguish when we're inside a class that has a superclass versus one that doesn't. When we resolve a class declaration, we set that if the class is a subclass. So in visit class statement, we're doing this. If statement superclass is not null, then resolve the subclass, and that is here. We can just do it right at the top, right? So it's setting current class, but when does it switch it back? In the super expert, we check. Right, it needs to switch it back to here. Right, because here what I do is I say let enclosing class is equal to, oops, what am I doing? Let enclosing class is equal to self current class replaced with this. So now we have the enclosing class is going to be whatever was there. Then at the end of visit class statement, we replace it back with the enclosing class. Oh, I see what we're going to do. We're going to say, okay, well, I thought it was going to be a class, but it's actually a subclass. And so enclosing class still captures the previous environment, or the previous scope, I guess, class scope. And it'll still put it back to what it's supposed to be. So we can just ignore the whole thing and say, if this, then self current class replace class type subclass, right? And then This down here will do the right thing afterwards. We're going to ignore the fact that we shoved a class in there. It's actually going to be a subclass. Okay, and then visit super expression. We're going to look. We're going to check the current class type. I guess we can use match. Self class, the current class, borrow. Class type, none. Self error, expert keyword, can't use super outside of a class, right? If it's class type, class type, this is saying not equal to subclass, then it's an error. Subclass, then we can ignore it, and then class type. Oh, then we can just do anything else, right? So this is the not equal to subclass clause. We can say self error expr keyword can't use super in a class with no superclass. Is that it? I think that's it. Oh, I got resolve local. I wasn't supposed to do that. Doesn't like this. Oh, I have to surround it with a body. Oh, because of the semicolon. But we can get rid of the semicolon and change it to a comma. Still didn't like it. Oh, okay. Because the arms don't match now, right? Yeah, okay. Let's just do it the old-fashioned way here. No, it still doesn't like it. Oh, it has a there. Okay. That's fine. This works. All right, let's see if this catches both of those conditions. Cargo, run. Super foo. Can't use super outside of a class, right? And then this. Can't use super in a class with no superclass. Perfect. Gets this. Git add, generate, and source. Git commit -m 13.3. What was it called? Super? (13.3) was calling superclass methods. Nice. All right, that's that. And then we're done, right? I think we finished. Conclusion. We made it. The final bit of error handling is the last chunk of code needed to complete our Java implementation of locks. This is a real accomplishment and one you should be proud of. I am very proud of myself. What else did we have? We should check to make sure all these locks things run. Right? Even whatever pathological is. The other thing I need to do is get the tests working again. Because if I say cargo test, everything blows up because I changed the interface. Or I should just rip them out because I'm not even using them. It would be nice to rewrite this book. Oh, Alvaro Falante says, I'm a programmer and also a farmer. I have pepper plantation. Oh, nice. 3,000 square meters of land. Not much, but enough. I don't think I could survive on peppers all day, but hopefully you can trade with your neighbors and get get something other than peppers to eat. I don't have enough land to subsistence farm anyway. So anyway, Yeah, so maybe it's just time to rip out these tests. Like I was saying, I think the ideal thing to do would be to rewrite this. If we're going to do it in Rust, is just do it as a test-driven development kind of thing. What else? What other things have tests? All the environment tests pass. Okay, that's good. But it would be nice to do. Vor says spicy life. Yep, that's good. I mean, that's a great way to live, right? Okay, so in the past dozen chapters and 1,000 or so lines of code, all right, let's push that up. Let's take a look here. We're actually, oh, that's the RLTK tutorial, which I'm going to do next week. But this week we're doing, oh, it's April Fool's Day. How annoying. Okay, so tokens and lexing, abstract syntax trees, recursive descent parsing, prefix and infix expressions, runtime representation of objects, interpreting code using a visitor pattern, lexical scope. We actually had to go through this. We had to make a few passes on this to get this working. Lexical scope, environment change for storing variables, control flow, functions, parameters, closures, static variable resolution, error detection, classes, constructors, fields, methods, and finally inheritance. We did all of that from scratch with no external dependencies or magic tools. I have 0 dependencies. Look at that. Just you and I, our representative text editors, a couple of collection classes in the Java standard library, and the JVM runtime. This marks the end of part 2, but not the end of the book. Take a break. Maybe write a few fun LOX programs and run them in your interpreter. You may want to add a few more native methods for things like reading user input. All right, so since we're done, LOX supports only single inheritance. If you add a feature of multiple inheritance, like there's mix-ins, traits, multiple inheritance, virtual inheritance, extension methods, etc. I don't have the brain power to think about that. In LOX, as in most other object-oriented languages, when looking up a method, we start at the bottom. Language beta takes the opposite approach. When you call a method, it starts at the top of the class hierarchy and works down. So how do you override methods then? Oh, the superclass method controls when and where a subclass is allowed to refine its behavior. Take out the LOX's current overriding and super behavior and replace it with beta's semantics. Huh. So donut always has frying to golden brown, calls the inner, which says pipe full of custard, and then place in an icebox. In the chapter where I introduced LOX, I challenged you to come up with a couple of features you think the language is missing. Now that you know how to build an interpreter, implement one of those features. What's missing? Random number generator. Rust doesn't have one built in, right? It would have to be a dependent crate. Yeah. I'd have to add in the ran to crate. Okay. All right, and then so starting in, I think, 3 weeks, based on my calendar, what do we got? Today's the 1st. Okay, so next week, the 4th through the 8th, I'm going to be working on finishing up the roguelike tutorial in Rust. We're almost done. We're so close. We're going to start logging, or we're partway through logging, right? The system's broken right now. And then text layers, systems dispatch, Dark Elf City 1, Dark Elf Plaza. And then there's going to be one more chapter, but that's not going to be for a while. So that'll be that week. And then the following week, I'll start bytecode virtual machine, and then I have a week off. Spring break. Okay, so that's the way things stand. Is there a way to get Cal to show the week properly, or the months properly? No. I just wanted to start on a Monday. That's the way I do my calendar, not the Sunday business. All right. So I think we're good. So next week, we're going to continue with the Rust roguelike tutorial. If I can get the tab to show up and get the logger working. We were partway through this, and it's kind of in a broken state right now. Yeah, there's all sorts of errors that we need to clean up because we changed the interface for it. And I have to remember how it all works. And then we'll finish that up, the roguelike tutorial, and actually have a roguelike game to play, which is right here. And that'll be, wow, there's a lot of townsfolk. Why are they disappearing? That's weird. I think there's a bug somewhere. You see how many townsfolk there were? When I came out, there were millions of them. And then as I walked, they were becoming invisible. All right, I'm not going to worry about it. That's something for next week. Meanwhile, I had a great time with this. I really enjoyed the AST version of the locks language, and bytecode in 2 weeks or a week and a half, actually. Thanks for hanging out with me, everyone. I hope you enjoyed it, and I will see you on Monday. All right, take care.